Okay, this section is on the electric potential, sometimes known as the voltage, colloquially, widely known as the voltage. So we've already talked about electric potential energy, and it comes from really the general definition of potential energy, where if you say work is equal to the integral of force dot dl, right? If you remember from back in the old days, work was equal to force times distance times cosine of theta, and that's true if those two things are kind of straight lines. But if the force varies and the length in the path is not straight, you really have to turn that into an integral. And of course, the cosine is in the dot product in this integral. And so this can be any force and the work done by anything. When we're talking about conservative forces, sometimes we define a potential energy and we can say the change in potential energy is equal to the negative of the work done by the force. And what that means is that when gravity is doing negative work, when you're raising an object against gravity, gravity is doing negative work, you're doing positive work lifting the object, and therefore the potential energy is increasing. So the potential energy is just the negative of what the work the gravitational field is doing. If the gravitational field is doing negative work, your potential energy is increasing. Because then later you can have it do positive work by dropping the thing, right? And so you can say it's minus the integral of f dot dl. Right? In the context of electrical stuff, we say the change in potential energy is equal to minus the integral of f dot dl. But if we're talking about electric fields, we define the electric fields this way. We said it's minus the integral of q times the electric field dot dl, right? Because the field is doing the work on a charge. And so we can write it this way. If the charge is constant, it's minus q times the integral of E dot dl. And that's the potential energy. And if it's an electric field, we would call that the electric potential energy. And we've already talked about that for a point charge, say. But now the way we define the voltage or the electric potential, it's the potential energy per charge. In other words, the voltage change, or the electric potential change, is equal to the change in potential energy divided by the charge. And so that's equal to minus q times the integral of E dot dl over q, or just minus the integral of E dot dl. And so it'll often be written as either a delta V or a V. Sometimes you'll just see the voltage is equal to minus the integral of E dot dl. And so this is just sort of a general definition for the electric potential. So if we want to talk about the electric potential due to a point charge, we can have a little point charge here. And then we know that V is equal to minus the integral of E dot dl. Sorry, not necessarily around a closed loop, just minus the integral between 2 points. And often we'll write this as between a reference point and a point P. So we might say minus the integral from R reference to P to some point P of E dot dl. And we know that the electric field always points radially, right? And so the electric field, if this is, we'll just say this is Q greater than 0, right? the electric field points outward everywhere. And so anytime I'm moving perpendicular to the radius, in other words, I'm moving in a circular direction around the center, the dot product of the electric field and the dl is 0, right? Because they make a 90-degree angle. If I go this way, if dl is pointing this way and E is pointing this way, then the work done going in that direction is 0. In fact, if I go this way, say my dl is in this direction, right? Then it's just a component of dl that's parallel to the electric field at that point that for which work is done. And so when I evaluate this, I really just need to look at the change in the radial distance. And so I can really write this as v is equal to minus the integral from r ref to, say, some radial distance, r sub p at point P, of E times dr, where dr is the radial distance that I change, because the angular distance that I change doesn't matter in this case. And so the electric field for a point charge is just is something we already know, right? It's kq over r squared, and that's times dr. And so we can evaluate the electric potential from some reference point to some point q, and maybe I should be calling this a delta V again, but this is a difference, right, between 2 points. And this is in the same way that I calculate a potential energy. This is a potential electric potential difference. It's not an energy, but it's a potential difference. And so this is just minus the difference between evaluation at r ref and r sub p, my point of interest. So the integral of kq over r squared, well, the k and q are just constant. It's the integral of r squared is minus 1 over r. Right? If you take the derivative of this, you get minus 1 over r. You get 1 over r squared. You get a minus 1, and that one cancels that one. And so we get the minus signs cancel, and I get the evaluation from r ref to r sub p of kq over r, and so that's kq over r sub p, my point of interest, minus kq over what my reference point is, wherever I started from. Usually what we do is we say, just as with potential energy, you're always talking about a difference when you're talking about electric potential. Whenever we're talking about potential energy, we're always talking about a difference in potential energy between the floor and the top of the table, or wherever the object falls from. It's convenient, because of the nature of this form of the equation, to say, look, we're just going to call b equals 0 at a reference relative to infinity. Because if you evaluate kq over r at infinity, you get 0. And so that's just a convenient place to always choose our 0. And so this says the electric potential at some point due to a point charge is just kq over wherever that point is. And so this is the evaluation of the electric field due to a charge q at some point r. So for example, let me just erase some of this here. So this is asking, what's the electric potential? In other words, what's the voltage relative to infinity, a distance of 10 to the minus 10 meters from a proton? Well, the electric potential for a point charge is kq over r. And so this is 9 times 10 to the 9th Newton meter squared per Coulomb squared times 1.6 times 10 to the minus 19th coulombs, because that's the charge on a proton, divided by 10 to the minus 10 meters, right? I get about 14.4 volts for that. So that's what the electron, that's the voltage the electron is living in, relative to infinity. So let me do another example. Hang on a second. So if I were to draw this, I might say, look, all right, here's my z-axis, and there's my Q1, and here's my Q2 right here, right? And then 1, 2, 3. I'm asking, what's the electric potential there, right? If this is my x-axis, right? And so the first thing to know is that the total voltage is just the sum of the voltages due to the individual charges, and that's just KQ1 over R1 plus KQ2 over R2, where this distance is R1, right? And this distance is R2. So R1 is equal to 0.03 meters, right? Because I put it at x equals 3. And R2 is the square root of 0.03 meters squared plus 0.04 meters squared, all square rooted, right? You might recognize that as a 345 triangle, so this is 0.05 meters. And so that's my R2. So my total voltage, V tot, is just equal to K times Q1 over R1 plus Q2 over R2. Right? And that's equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared times 3 times 10 to the minus 9th coulombs divided by 0.03 meters plus, and this guy is negative 3 nanocoulombs, so it's minus 3 times 10 to the minus 9 coulombs divided by 0.05 meters. And what I get when I evaluate that, what do I get when I evaluate that? 360 volts. So the electric potentials add. If I had 4 charges here, I could just add up the electric potential due to each one as though they were living all independently. So if you recall, when we were looking at electric fields, we have first evaluated the electric field due to point charges, and then we did a line of charge and a ring of charge and so on. And we want to do the same thing with electric potential. We want to be able to talk about what's the electric potential due to a line of charge or a surface of charge. And so we're going to start by saying what we just said a minute ago, that look, the electric potential due to a bunch of charges is just should be an I. If we want to do continuous charges, for continuous charge distributions, we have to do something that looks like this. We say, look, it's K times the integral of dq over r. So rather than having a series of discrete point charges, I have a whole bunch of point charges that are dq's. And then I have to go back to this approach that we used over on electric fields, where he said, look, dq is equal to lambda dl for 1 dimension, sigma dA for 2D, and rho dV for 3D, right? In each case, this is lambda is the linear charge density, sigma is the surface charge density, and rho is the volume charge density, right? And just depending on how we have to define our Q, what our problem looks like, we have to pick one of these and use it. So just to draw a picture here, I've got some, here's my z-axis, here's my point P, this distance here is z, right? And this distance here is L, right? And this is my length L. And then here I've got a little dx here, and this has a little amount of charge dq, and it's equal to lambda dx, right? It's the linear charge density times the if this distance is x, then r is equal to the square root of z squared plus x squared. And then we can say, look, we can say the electric potential at the point P is equal to the integral of k dq over r, where we integrate along this line, right? And so I can say my integral is from minus L over 2 to L over 2. Now my integration variables are not all x or anything, and so I have to be a little more sophisticated in how I do this. And I can say, well, really, this is an integral from minus L over 2 to L over 2 of k times, so my dq is just a lambda times dx. That's what my dq is. And my r, I can clean that up a little bit, k. My r is the square root of z squared plus x squared. Right. And so if I do a little work here, I can pull out my constants, say lambda times the integral from minus L over 2 to L over 2 of dx over the square root of z squared plus x squared. It turns out you can evaluate this. You can also just look it up. Remember, z is a constant, right? Z is just how far I am above the wire. It's the same for the whole integration. The distance z does not change for my integration. And so you can evaluate this, and you get Vp is equal to, so k lambda times the evaluation from minus L over 2 to L over 2 of log of x plus the square root of x squared plus z squared. And so if I erase some of this now to give myself some room, so hopefully I guess you can just scan back and pull that image up if you need to. But if I evaluate this at the two endpoints, I get Vp is equal to k lambda times the log. Let me do it this way. So I'm going to evaluate it here, and then I'm going to subtract the evaluation there. And so I get the log of L over 2 plus the square root of L squared over 4 plus z squared minus log of, this is minus L over 2 plus the square root of L squared over 4 plus z squared. And I'm going to have to erase a little of this too, I guess. I can just, the log of the difference is just the same thing as the log of the ratio. And so this is going to be a little ugly, but L over 2 plus the square root of L squared over 4 plus z squared over minus L over 2 plus the square root of L squared over 4 plus z squared. And I can simplify this just a little bit by multiplying the top and bottom by 2. I can just multiply this thing by 2 over 2 inside the log, and I get k lambda, not a significant change, but it looks a little cleaner, of L plus the square root of L squared plus 4z squared over minus L plus the square root of L squared plus 4z squared. And so that's the electric potential at for a charge distribution that's just a length L wire, or I guess I wouldn't call it wire. It's a material that has a uniform charge distribution lambda and has length L. So let's look at, just as a little digression, this was the electric potential due to the, at a point, due to a line of charge length L at a point Z above the line of charge, above the midpoint of the line of charge, and we got this complicated formula. And so we want to analyze this for Z much greater than L, so that, you know, here's your line, and now you're way up here, you're really far from it, somewhere way off the chart, say, or maybe it was over here, and that's where you are out there, or something like that, right? We want to look at for a really large C, and we want to show that this will look like a point charge formula. And there's a little work to get there from here, and you'll have to stay with me for a minute, but I can just look inside this log function, right, and say, well, if I divide through by Z squared over 4 inside, or Z over 2 outside, sorry, 2Z, right? I'm going to divide by 4Z squared inside and 2Z outside, right? So I multiply the top by 1 over 2Z, and then when I get inside the bracket, it's 1 over 4Z squared. And the same thing on the bottom, 1 over 2Z. So I'm multiplying top and bottom by 1 over 2Z. Inside the radical, it looks like a 1 over 4Z squared, so this becomes plus the square root of L squared over 4Z squared, right? Because I'm dividing that by 4Z squared because it's inside the radical. It would be 1 over 2Z on the outside plus 1, right? Because that guy just becomes 1. Similarly, here I get minus L over 2Z. I do top and bottom, so I'm just multiplying by 1, right? I'm multiplying by 1 over 2Z inside the bracket on top and bottom, so I'm just multiplying by 1, right? Plus the square root of L squared over 4Z squared plus 1 again, right? That's what my bracket looks like now. And so in this limit, and I won't break these down, I could a little more carefully, but I won't break these down. This is just L squared over Z squared, but for Z much greater than L, I can neglect this term relative to that. And so that one goes away, and that one goes away, and it's the square root of 1, which is just 1. And so this becomes K lambda log of 1 plus L over 2Z over 1 minus L over 2Z. And if you have 1 over 1 minus alpha, where alpha is much less than 1, that's approximately equal to 1 plus alpha. And you can do it, you know, so if alpha is, say, 0.01, 1 over 0.99 is approximately the same as 1.01. And you can check that for yourself. But you should, on these little approximation things, you should verify them with some examples on your own. And you can put in numerical examples for these, right? And so this becomes K lambda equals, K lambda times the log of 1 plus L over 2Z times 1 plus L over 2Z, where I've replaced this 1 over 1 minus L over 2Z with this philosophy as a 1 plus L over 2Z, right? And so my VP down here becomes K lambda log, and so it's 1 plus 2 times L over 2Z plus L squared over 4Z squared, Z squared. But I'm already ditching these guys. I've already agreed to that. And so this becomes K lambda log of 1 plus L over Z. It turns out that if you do a series approximation to this thing, the log of 1 plus L over Z, you can represent it approximately. So I'm just going to have to go back up to the top. This is just another Taylor series approximation. So this is the term we're looking at. Again, we're evaluating Z much greater than L, right? And we're reduced to this. You know, by simplifying the algebra in here, we end up with a 1 plus L over Z. If you look at a series expansion for logarithm in the vicinity of 1, you get something that looks like this. Notice if this quantity is x, x is pretty close to 1, right? Because L is small compared to Z. So this is a number just a little bit over 1. And so it means this is a small term, and this is a small term squared. So we're just going to keep the first term, and we're going to say, look, Vp is equal to k lambda times, instead of log of 1 plus L over Z, we're just going to have 1 plus L over Z. That's the x, that's what's inside the bracket, minus 1, which is equal to k lambda L over Z. And notice that k lambda is just q, right? Because the charge per unit length times the length is just the charge. And Z is how far away from you are, how far away from it you are. That's the electric potential of a point charge. So now we're going to do just as we followed along the procedure with the electric field. We're going to say and so we're going to draw a ring of charge here. And this is our point, this is our z-axis, this is our point P, something above the z-axis. This is my, I guess, my y-axis, and this is my x-axis if I'm going to do it like that, right? And then if I have let me draw a bigger ring. So I have a little more room to draw. Right, then this is my theta, and this is d theta. This is a length. I can say like dl or something is equal to r d theta, right? In sort of the in the radians language, right, where the radius of this ring is big R. And so dq is equal to lambda dl, or lambda times r times d theta, right? And if you'll notice, like every little piece of ring around here has r is equal to the square root of r squared plus z squared. Right, now as I go around the circle, that doesn't vary because the radius doesn't change. This is r, and this height, it doesn't change. That's z, right? And so I can say, look, the electric potential is the integral of k dq over r, and that's equal to the integral of k lambda dl over r, right? And that's equal to the integral of k lambda r d theta, because that's what my dl is, right, over, if I want to, I can say the square root of r squared plus z squared. But notice all of these guys, the r, the big R, the z, the lambda, the k, they're all constants. And so this is just the integral around the circle of k lambda r over the square root of z squared plus r squared, or r squared plus z squared, of d theta going around the circle, but the integral of d theta is just 2 pi. And so the electric potential is just k lambda 2 pi r over the square root of z squared plus r squared. And that's just kq over r, right? If you remember doing the electric fields, after we did a ring, which was pretty easy in that one as well, then we did a disk, and so we'll do that here also. So in this problem, we're going to look at the electric potential Vp at a distance z above the center of a disk of radius r with a surface charge density of sigma. And so the black ring is my disk. That's my charge. That's my disk that has a surface charge density of sigma. I'm going to evaluate it by integrating outward from the center with these rings. We've already determined what the electric potential is due to a ring. But this time, instead of that being the whole potential, I'm going to say, look, dVp, in other words, the contribution to the electric potential at the point P due to one ring is just equal to the evaluation we did in the last section. I'm using a capital Q for some reason on this one for the whole plate. And so I'm going to call this r prime. R prime is the distance to the ring, and it's equal to the square root of r squared plus z squared, where r is the radius of the tree ring that I'm doing, and z is the distance that we are above the center of the ring, that our point P is above the center of the ring, right? And so I could rewrite this if I wanted to as k dq over the square root of r squared plus z squared, like that. This dq is a little bit of a question, right? Because q is the total charge on the plate, and so q over pi times big R squared, the radius of the disk, is just my surface charge density, and so I can say q is equal to sigma times pi r squared, or I can say for this little ring here, I can say dq is the area of the ring, which is sigma times 2 pi r times dr. 2 pi r is the circumference of the red circle, the tree ring that I'm integrating, and dr is its thickness, right? And so I could rewrite this dVp as equal to k. Instead of the dq up here, I'm going to put sigma 2 pi r dr over the square root of r squared plus z squared, like that. And then I can say Vp is equal to the integral of dvp, where I'm adding up all the tree rings, right? I'm going to pull everything that's constant outside, and so this is 2 pi sigma k, right? That's this guy, this guy, this guy, and this guy, times the integral from 0 to r of r dr over the square root of r squared plus z squared. And so I'm going to do this integral by substitution. I can just look it up, but we'll do it by substitution. We'll say, look, u is equal to r squared plus z squared, du is equal to 2r dr, and so r dr is equal to du over 2, and so this vp becomes the integral from 0 to r, and I won't make the substitutions yet, but I'll do on the limits, but I'll do it in a little bit. The numerator becomes du over 2, and the denominator becomes u to the 1/2. Ooh, I lost my terms there, so I'll just put them on the outside, right? This is 2 pi sigma k, right, like that. And so this becomes, I'll just put it back in the front now, 2 pi sigma k times the integral of this is the evaluation from 0 and r of the integral of u to the minus 1/2 is u to the 1/2 over 1/2, which is 2 pi sigma k times the evaluation at 0 and r of 2, 1 over 1/2 is 2, right? Times r squared plus z squared, so 1/2. Okay, I have a little error here. I lost this 1/2 here. I got the 1/2, this 1/2 from the integration process, but I lost my du over 2, so there should be a 1/2 here, and there should be a 1/2 here, and that'll cancel that. And so I just end up with 2 pi sigma k times the square root of r squared plus c squared minus c.